Boys and girls, ladies and gentlemen, please welcome Professor Bassam Shakhashiri as he presents his 21st annual Once Upon a Christmas Cheery in the Lab of Shakhashiri.
Thank you very much. Thank you very much, everyone, and welcome to my lab. I'm delighted to see you here tonight, and I promise you a good time. I want you to be as attentive as possible and be always on the lookout for all kinds of changes in color. Be on the lookout for smoke. Be on the lookout for fires. Be on the lookout for explosions. And I want you to sit back and relax because we're going to do all these experiments in a very safe way. And you'll see that I'm going to put my eye protection on right away. And I want you to see that I have a fire extinguisher ready to be used just in case something does go out of control. You know, in the laboratory, we always do experiments in a very safe way. And we always have to obey the safety regulations. The special theme of the lecture this year is carbon dioxide. And we're going to talk about the chemistry, the physics, and even the biology of carbon dioxide. And we're going to have some very special guests, not only from the University of Wisconsin-Madison, but from around the world, as you will see shortly. So now I want you to realize that chemicals are all around us. Everything that is around us is made up of chemicals. That's why chemistry is a very important topic to know about. The air that we breathe is a mixture of chemicals. The food that we eat is nothing but chemicals. The medicine that we take when we're sick is also chemicals. The drugs that some of you very foolishly experiment with are chemicals. And so we have to understand what the chemical properties are, what the behavior of chemicals are, what their benefits are, and how we can safely handle them. So, to begin with, we're going to carry out some experiments in this Christmas lecture, which is in the tradition of the great British scientist Michael Faraday, who over a century ago did a very special program for children of all ages at the Royal Society in London. And his program was on the chemistry of the candle. And right here you see an example of what we call a combustion reaction. This is when something combines with oxygen that's in the air and it burns. Did you ever wonder why the candle stays lit? Why does the flame have the shape that it does? Does the color of the wax have any effect on the color of the flame? There are a whole bunch of questions that we can ask and a whole bunch of questions that we can think about. And that's what we do in science. Ask questions, make observations, and try to make sense out of these different observations that we make. So I told you to be attentive and to be on the lookout for all kinds of changes. I am going to take something out of my wallet now. I'm going to take a dollar bill and put it on top of this flame. Did you see that? See that I told you have to be very attentive because these things happen sometimes very, very fast. So we'll take another dollar bill. Actually, it looks like a dollar bill, but it's not a dollar bill. This is specially treated paper. It's treated in such a way that when it burns, it leaves no residue. And so we'll do this experiment again because that's what we like to do in science. Repeat the experiment to validate our observations and see if they make any sense. So watch. See what happens. And there, the dollar bill disappears. Now I'm going to take a real $20 bill. This is for real. And we'll carry out an experiment with this one. And this experiment we'll do by dipping the dollar bill in this liquid that's in this beaker. We'll uncover it. And we take the $20 bill and we dip it in. I try to fish it out with these tongs. Make sure it's all wet. You see, it's all wet. Right? See that? And now we're going to try to burn it and see what happens. You see it on fire? But it's still intact. And it is a good, it's a good $20 bill. I'm going to save it and use it to buy Christmas presents with it. This paper was dipped into this solution that has in it a mixture of alcohol and water. And it's the alcohol that burned, not the paper. The alcohol burns at a lower temperature than the paper, and that's why we saw the flame coming from the burning of the alcohol, not from the burning of the paper. So we're going to put this back because I told you I'm going to use it. It is an honest-to-goodness $20 bill. And now we'll move on and do some other experiments. But before I do that, it is getting a little bit warm in here because of these combustion reactions we're doing. So I'd like to take off my jacket. Would that be all right if I did that? Okay. Before I do that, I want you to know that the purpose of this presentation is to convince you that science is fun, as my button says. Fun in the best sense of the word, not in some cheap thrill fashion. And that's why I want you to be paying attention to what we do. Okay, so we take my jacket off, and I'll put it away here. How about if I take my tie off? Would that be all right? It is a little warm in here. So I'll take my tie off. I've got to take this. How about if I take my shirt off? Would that be all right? Okay. I really want you to be convinced that science is fun, and that's what we're going to try to do this evening, I and my special guests. So we'll go on with these different experiments that relate to combustion, which is the combination of something with the oxygen in the air. And what we're going to do next is take a long burner that's connected to a source of gas that burns. You know, some gases burn and some other gases don't burn. We'll put this on. You see there's a flame. Can you see the flame? It has a special shape. It has a special color. And what we observe here is that energy is released in the form of light. We see the flame. And we know from experience that this also gives off heat. We call this an exothermic reaction. And as I mentioned, some substances combine with oxygen and burn. Some other substances don't. So I'll put this down here for a second like so. And I know that when you came in, you saw a lot of different things on the lecture table. You also saw these balloons that we have up here. What do you suppose we have in those balloons? What? Just tell me what. Now you know, some of you are saying helium. You know why you say helium? Because you know from experience that helium-filled balloons are lighter than air. And that's a key word, experience. You always learn things and you should use what you learn. So let me tell you that helium is a gas which does not burn. Helium is a gas that if I were to put this flame to a balloon that has helium in it, it will not burn. So one way in which we can find out what's in these balloons is to try to ignite them. So we'll start off with this balloon right here. And you see all that has happened is that the balloon popped and the flame went out, so I'll relight that flame. That balloon had in it helium gas, and helium does not burn. We'll move on to the next balloon that we have over here, and we'll try to find out what's in it. So you're ready? So now, did that balloon have helium in it? That balloon had in it a gas which is lighter than air, but also a gas that combines with oxygen. That gas is hydrogen gas. And what we're going to do next is repeat the experiment, but we're going to do it in the dark with the lights off. We're going to repeat this experiment and see what happens, what we can look at. Ready? Here we go. Now with the lights back on, with the lights back on, we confirm that hydrogen-filled balloons are very dangerous when they are subjected to an ignition source. And what we should do now is ask you to look at the monitor and watch the same combustion reaction in slow motion. You won't hear any sound, just watch it. The flame will be coming up pretty soon. There it is, and there is the big ball of fire showing the combustion reaction of hydrogen with oxygen that's in the air. Now you noticed, as we were carrying out this experiment, that the intensity of the sound energy that's released increases as we go from the helium-filled balloon to the hydrogen-filled balloon. And so before we go on to the next experiment, and because we want to be doing experiments in a safe way, I would like you to protect your eardrums from potential damage by taking both fingers and sticking them in your ear very, very tightly. Now you see, I can't do that and do the experiment, so I have some earplugs which I will put in my ears and carry out the next experiment. If you can hear what I'm saying, that means you don't have your ears well protected. I can't hear you, but I can see you smiling. It means you heard what I just said. Please protect your ears as carefully as possible as we go on to the next balloon. Now, that balloon had in it a mixture of hydrogen and oxygen, and that's a very, very dangerous mixture. What we're going to do next is repeat the experiment, but do it in the dark. So again, plug your ears as carefully as possible. The lights on. Now let's take a look at the monitor again and see this in slow motion and see if there's a difference in the brightness of the explosive mixture that we have. There's the flame from the torch coming up to the balloon. You won't hear a sound, and you see the big ball of fire. The red balloons had in them a mixture of hydrogen and oxygen, a very dangerous mixture that we should keep all sources of flames away from. Now, I said that carbon dioxide is the main theme of the presentation this evening, and carbon dioxide, of course, at room temperature is a gas. It's a colorless, odorless gas. We can't see it and we cannot smell it, but it's a gas that is involved in photosynthesis. Plants need carbon dioxide, and we will do some experiments later on with plants. Carbon dioxide itself does not support combustion, so carbon dioxide does not burn, and carbon dioxide exists also in the form of a solid. And I'm going to take a small amount of this solid, which we call dry ice. I'm going to put a chunk of this dry ice right here, and you can see it very closely. It's white, and it changes from being a solid to being a gas directly. It sublimes. Its temperature is minus 78 degrees Celsius. You know, in science we keep track of temperature in the Celsius scale, not in the Fahrenheit scale. So its sublimation temperature is minus 78 degrees. And we're going to do experiments with solid carbon dioxide. We're going to take a whole chunk of set of chunks of carbon dioxide in the solid form, and I'm going to simply grind them like so to make powdered carbon dioxide. And in this powdered form, there's more surface area, so the sublimation rate is faster than it is when I have the chunk of dry ice. Notice I'm wearing gloves to protect my hands and from frostbite. we always have to be obeying the safety regulations as we do these experiments. Now, some of these experiments are going to be done by my taking some of the dry ice powder and putting it in this balloon. You see what I'm doing? I just take the chunks of dry ice in the powder form. I have a funnel. I put it in this balloon. And I fill the balloon with powdered dry ice. I'm going to close off the balloon. And we'll just put it here and see what happens. Now, I want to show you another property of carbon dioxide. And let's see if we can do this by taking, you keep an eye on that balloon, by taking some of the dry ice, putting it in this beaker, and just wait for a few seconds or so. Then we take this beaker and we try to pour. See, the flame went out. Let's do it with this one. Again, giving us evidence that carbon dioxide does not support combustion, does not burn. So let's try it one more time. And the carbon dioxide gas is coming from the sublimation process. Here we go. Do it one more time. See? That's why we have carbon dioxide fire extinguishers. And they are useful for certain types of fires, not all types of fires. Now, carbon dioxide is in the solid form. And what we're going to do next is take chunks of dry ice. And I want you to focus your attention on this part of the lecture table where we have these glass cylinders that have the colored liquids in them. And I'm going to do an experiment in a very special way. You make the observations and tell me what this special way is. I take chunks of dry ice and I drop them in. You see a lot of interesting things happen. You see the bubbles of gas. That's the carbon dioxide gas. And it's in some cases there you see a color change. In other cases you don't see a color change. What's this stuff coming off the top here? What? No, somebody said it's carbon dioxide. Remember, carbon dioxide is an invisible gas. You can't see it. What does it look like? It looks, somebody said steam. You know, steam is an invisible gas. You can't see that either. Come on, you tell me, what does it really look like? It looks like fog. You're right. That's what it is. You know what fog is? Fog is condensed water vapor. So the water vapor is condensing on the carbon dioxide that's escaping. And the movement of the fog is in a downward direction, once again reminding us that carbon dioxide is heavier than air. And so that's why I was able to pour the carbon dioxide out of this beaker and put out the candle. Now, there are other experiments that we can do. And to do this experiment, I need some hot water. Let's see if I can find some hot water. Can somebody bring me hot water, please? Ah, thank you, Bucky. Bucky Badger has been a chemistry student for 21 years. I want you to know that Bucky is a very good student. And Bucky has been busy this weekend and practically every day with supporting and cheering on the volleyball team and the basketball team and, of course, the hockey team. And Bucky has taken time out to come once again to this very special anniversary lecture. And I thank you for that, Bucky. I thank you for doing that. And I just wonder, do you have time to stay, Bucky? Can you stay? Would you like Bucky to stay? All right, I have a special place for you right there. There's a chair for you right there, Bucky. Make yourself comfortable. And with this water that Bucky brought, this hot water, I'm going to pour it into this empty dishpan. Okay, so here it goes. You see anything coming off the top? What do you see? Oh, please don't say steam. Steam is invisible. What you see is condensed water vapor. What we're going to do is take a whole bunch of dry ice and put it in there and see what happens. Now, this is how they make fog in the movies sometimes. And you see the movement again is in a downward direction, reminding us that carbon dioxide is heavier than air. And the condensation is taking place on the carbon dioxide that is escaping. And this will stay like that for a while until the carbon dioxide all is changed. Now, the temperature in here is very, very cold. It's minus 78 degrees Celsius.
Merry Christmas!
We have another visitor now.
Merry Christmas! Ho, ho, ho! Merry Christmas! Merry Christmas! Ho, ho, ho! Merry Christmas! Merry Christmas!
Hello, Santa.
Good to see you, Dr.
Good to see you.
Shakhashiri.
And
How are you
welcome,
doing?
welcome to my lab. I'm doing fine.
Yeah.
I've been good all year long.
You've been good all year long?
I've been very good all
Well,
year
I brought you a very special present today.
You did.
Yes.
I hope it's what I asked for.
Well, I hope so too.
Oh my goodness.
What do you think?
Look at that. I love it. Look at this.
Isn't that
Look at
beautiful?
this, everybody. Isn't that
Yeah.
neat? Ah, thank you, Santa. That's very nice.
I also brought you another present.
You did?
Yes. A bag full of experiments to do.
My goodness. You and your elves have been very,
We've
very
been
busy,
very busy.
right? Can I
Yeah.
peek in there and see what's in there?
Yeah.
Oh my goodness. Here's a Science is Fun button.
Yeah.
All right. And here's a light stick. And here's some instructions for doing experiments at home.
Would you boys and girls like one of those? I brought enough for everyone.
All right, Santa and his elves brought one for everyone that is here. And can they pick them up on their way
Yeah,
out
pick
then when
them
they
up on
finish?
the way out, yeah.
Right. And for all right. Now, Santa, let me ask you for the people watching on television, if they want to get this, can they get some of the copies of the instructions from the Institute for Chemical Education?
They certainly can.
They can write to the Institute for Chemical Education right here at the University of Wisconsin-Madison, and you can get copies of the instructions for these take-home experiments. Santa, I know you're very busy, but can you stay for this lecture too?
Well,
Please, pretty please.
well, okay.
You want him to stay?
Good.
Okay.
Okay.
All right.
I'll stay.
I'll have a chair for you right next to Bucky.
Next to Bucky.
Right next to Bucky.
Yeah. Good to see you, Bucky.
All right. Well, you never know. You never know who'll show up at this special Christmas lecture. I'm so proud to be doing this lecture for, as I said before, 21 years at the University of Wisconsin-Madison, and it is very, very delightful to see all of you here tonight. Now I'm going to take some more dry ice and carry out another experiment. This experiment is one actually that you can do at home, and I think Santa and his elves have the instructions for you in there. This experiment you can do in a fish tank like this. And what you do is you put some dry ice at the bottom, just like I'm doing here. Now you might say, well, how can I get dry ice at home? You can't get dry ice at home. What you really need is not dry ice. You need a source of carbon dioxide. And the way in which you can generate carbon dioxide at home is to take some baking soda and take along with it some vinegar. And you put the baking soda in a small dish and pour the vinegar on it in that fish tank, and you wait for a few minutes until the carbon dioxide saturates and fills that fish tank. The next thing that you do, and this is one of my favorite activities, is I take some soap bubbles. Don't you like to play with soap bubbles? Soap bubbles are so beautiful. If I can blow them first. There you go. They float. They have pretty colors on them. Now what you do is very carefully blow the soap bubbles on top of this aquarium. You see what's in there? Very gently, and you see the soap bubbles float in the carbon dioxide. Carbon dioxide is heavier than air. And if you watch carefully, are they still in there? Yeah, there's one in there. You will make a lot of interesting observations about the size of the bubble and about the colors that are on the bubble itself. And this is an experiment that you can do at home if you have a fish tank, a clean fish tank, if you have baking soda, some vinegar, and of course some soap bubbles. Now, in this part of the lecture, what I'd like to do is show you that carbon dioxide, which I told you already sublimes from being a solid to going into a gas directly, can be changed into a liquid. And to do that, I'm going to put my gloves on again, and I'm going to take some of the powder of the dry ice and put it into this plastic tube right in the bottom, fill it up about halfway. If you watch carefully, you can see the level of the solid inside this tube. And what might be of help is to put this, I have some more solid here. Okay, there it is. And the next thing I'm going to do is take this gauge and put it on top. And we'll watch what happens when the sublimation takes place inside this closed system. And we'll watch the pressure by looking at the pressure gauge. Tighten this. Now, is the pressure changing? Can you see the pressure changing yet? Not yet? Maybe I have to close this off first, see? Now it's open and I close it off. And we'll wait and see. This will take several seconds. We'll see what happens as the carbon dioxide sublimes. You can look very carefully at the pressure gauge. You can see that the pressure is changing. And we'll let this go for a while. And as we are waiting for this system to change, I would like at this time to introduce the person who is responsible for the very popular program called Wonders of Physics from the physics department, Professor Clint Sprott.
Well, here's a use of carbon dioxide I bet many of you haven't seen. It's a rocket-powered tricycle. You seen one of those? Santa's seen one. He has an even better way to get around. But that's what it is. This is an old carbon dioxide fire extinguisher mounted on the back of this tricycle, and I control it by right here. And it propels me very nicely. So this is a great application of carbon dioxide, but it also illustrates an important principle of physics that we call Newton's third law. Newton's third law has to do with the law of action and reaction. In order to make something go one direction, the tricycle in this case, something else has to go the opposite direction. In this case, it was carbon dioxide. Now, I want to show you another example of the law of action and reaction. This you can buy at a toy store. Maybe you have one even. It's a little rocket, and you fill it with water up to about that point, and you pump some air into it. So I'm going to do that. And then when I pump the air into it, I'm going to release it. The water is going to go out the back end, and the rocket is going to, propel all the way across the room. Now here's another cylinder. Here's another cylinder of the same carbon dioxide that I used on the tricycle. And this time I'm going to use it to do something rather unusual. I'm going to stand on a platform that can rotate around like this. And I'm going to set off the fire extinguisher and see what it does. Let's see if I can go the other way. So you see, this is another example of the law of action and reaction. When the carbon dioxide goes one direction, I go the opposite direction. Now, you know, there are many people that misunderstand rockets. A lot of people think a rocket, the exhaust has to push against something, like the air. Well, that's not right. Newton's third law says that it doesn't have to push against something. And I want to illustrate that to you in a very unusual way. You recognize this? What is it? Basketball. Sir in the red sweater, would you help me with this? Sorry to wake you, just stand up right at your seat. Because I wanted to do the following thing. I'm going to stand on the rotating platform. You ever played basketball? A little bit, good. So all I'm going to ask you to do is catch the basketball, and for the rest of you, I want you to watch what happens to me when I throw the basketball. You notice it makes me go around, and this is another example of action and reaction. The basketball went one way, I went the other way. Now just a minute. Let's see how good you are. Not bad. Now, we'd like to show you a couple of additional examples of this idea of action and reaction. And for this, we're going to bring some more equipment out here. And I'll bet many of you at home have a garden. Do a lot of you have a garden at home? Probably a lot of you have grass at home and where you live, right? In the summertime, sometimes do you put out a lawn sprinkler? Do you know what those are like? I'll bet you recognize right over in this corner a lawn sprinkler. Does this look familiar to you? That's just an ordinary lawn sprinkler. What do you think will happen if I turn on the water? Well, actually, we're not using water. We're using compressed air because we didn't want to get you all wet. But it's the same principle. It goes round and round because of the law of action and reaction, just like I did when I was standing on the rotating platform. Let me show you one other thing. Have any of you ever turned on the water to your garden hose without holding on to the end? What does it do? You're saying it with your hands. It goes round and round in a crazy way, doesn't it? Let's try that with compressed air. Did you know there's a name for that? That's called the fire hose instability. Can you imagine why they call it that? Because with the big fire hose that the firefighters have to use, if they ever turned on the water without holding on to the end, it could be very, very dangerous indeed. So these are some examples of Newton's third law, things that go round and round. Now I want to show you one other very curious example of Newton's third law. And to do that, I'm going to set a fire here in a thing that we call a Bunsen burner. So you see a nice bright flame, and can you see what's just above that flame? What does it look like? That's right, it's water. It's what we call a flask, and it's got a little bit of water in it, about 1 inch of water on the bottom. And I'm heating the water. What do you think happens to water when you heat it? Somebody said it boils. That's right. Water boils. Now, when the water boils, you notice it's starting to turn around. Why do you think it does that? That's right. The water turns into something. What does it turn into? Steam. Somebody said it. So it goes round and round. You know, this has a name. It's called Hero's engine. It's named after a scientist who lived about 2,000 years ago in Greece. And you know, back in those days, they only had one name because there weren't so many people. They didn't need two names. So he was just called Hero. He was Hero of Alexandria. And 2,000 years ago, he designed this kind of engine. A kind of engine that goes round and round, powered by nothing but heat and a little bit of water. Do you think that would be a good kind of engine to put in your car? No? Why not? Why not? Your car would go round and round. Well, I guess you'd have to hook it up to the wheels somehow. But you're right, it's not a very good kind of engine to put in a car because it's not very efficient. You have to use a lot of fuel and make a lot of heat, and it doesn't go around very fast, and it doesn't develop much power. So it would not be a good kind of engine for a car, but it does illustrate several important principles of physics and also of chemistry because it involves the boiling of water. Well, I want to show you just one last principle that really doesn't have a lot to do with rockets, but it does have to do with carbon dioxide. You recognize this? That's right. You know, this is called a carbonated beverage. Did you ever wonder why they call it that? No? What do you think it has in it? That's right, it has carbon dioxide in it. Now, there's a peculiar way we can show that it has carbon dioxide in it. I'll bet a lot of you have taken a bottle like this and shaken it and then opened it. What happens? It's very exciting, isn't it? But I'm going to do something a little different. I'm putting it in a little tray of water up here, ordinary water. And this water is in a tank. And it turns out this tank is a special kind of tank that we call an ultrasonic cleaner. Have some of you heard of that? They often have them in jewelry stores, and you put rings and jewelry in ultrasonic cleaners to clean them. But here we're going to put our little Coke bottle in the ultrasonic cleaner, and we're going to turn it on in a moment. I haven't turned it on yet. And what will happen is the water will shake back and forth because sound is a form of motion. When you hear something, it's because the air is moving back and forth, and it's making your eardrum move back and forth. So we're going to make the water move back and forth, but at such a rapid rate that you can't even hear it. So I'll turn it on, and we'll see what that does. So you notice, all the carbon dioxide came out of the beverage. And in fact, that's exactly the same thing that happens when you shake a bottle, except here we're doing it with these ultrasonic waves. Well, I hope to have convinced you that there's a lot of similarities between chemistry and physics and even biology. We all deal with things like carbon dioxide and so forth. And so at this time we'll talk a little bit more about chemistry, and then a little later in the day we'll come back and talk some more about what you can do with bottles of this sort. So thank you all very much.
Thank you, Professor Sprott. You know, we're very blessed at this university to have so many talented people who do not only excellent research, but do excellent teaching. And what I want to do now is ask you to take a look at the balloon that had the carbon dioxide in it. You see how filled it is right now. I also want you to take a look at the gauge reading. Look at the gauge reading and see that the pressure is really, really high. But we have this in a closed system in this tube of plexiglass. And if you take a closer look, you can see some liquid at the bottom of this closed system. Now this balloon will pop if all the carbon dioxide that's in here changes into a gas. But because the pressure here is in a closed system, the pressure is causing the carbon dioxide to liquefy. And if you look down there very carefully, like you were doing just now, you'll see that there's a liquid at the bottom of this tube. And when I release the pressure gauge, watch what happens to the liquid. It changes back to being a solid. So this is a way in which we can talk about the properties of carbon dioxide and the ways in which we can also deal with the properties of other substances. So I want you now to follow me as I'm going to do a very special salute to our two special visitors. By taking this spray bottle, oh, I'm not going to spray you, Bucky. Oh, no, Bucky. Just be calm, Bucky. Don't get too excited. But watch what happens here. You and Santa Claus, watch what happens when I spray this piece of white paper with this spray. And watch what happens down here. Now these pieces of white paper have been treated by using a brush, a paint brush, that was dipped in acid-base indicators. And acid-base indicators are substances that change color when the acidity or the basicity changes. And what I sprayed them with here is some household ammonia. So I'm going to do another experiment right now with some household chemicals. And these household chemicals are readily available. You'll see the first one I'm going to use is, what does this look like? It looks like cabbage. It looks like red cabbage, right? So what I'm going to do is cut this red cabbage and chop a piece off like so. Be very careful not to cut my fingers. And chop it into small cubes. I know some of you are thinking this looks like the Julia Child show, but it isn't. And the next thing I need is a blender. And I take these cubes and I put them in the blender. At least most of them I get in the blender. The next thing I do is I take some water and I cover the chopped cubes with water. What's the next thing I do, Bucky? Put the lid on, right? Put the lid on, right? Always obey the safety regulations. And then push the button. And you see what I've done? I've made myself now some red cabbage juice. And you might say, well, what good is this red cabbage juice? It can be used by you at home as an acid-base indicator to tell you whether some of the household chemicals that you have are acidic or basic. And what you need is a bunch of beakers like I have here, or some glasses or plastic cups. What you have to do first, though, is separate the finely chopped red cabbage from the liquid, and you use, what's this? A strainer. Everything I'm using you have at home, and so you pour it down like so. And you wait until most of the juice is down, and then you put this up on top so you don't make a mess. And I need more juice, I add more water to it. You see, and I've made myself now about, what does it say here? About 32 ounces, 4 cups of red cabbage juice. You know, in science, we use the metric system for making measurements, not the English system. So you can convert quarts to liters. Okay, the next thing you do is you put these, you fill these beakers about the same level with this liquid. Are they about the same level? How am I doing? All right. I hear Santa. He thinks I'm doing okay. Are they about the same level? Okay. Which one is high? No, this one is a little low, right? How about this one? Okay. Now the next thing you do is you take some household chemicals. What I have here is vinegar. And vinegar, we add it to the red cabbage juice, and you see we get this pretty red color. Then we take some household ammonia, and we add the household ammonia, and we get this color. And now we know the color of red cabbage juice when we have an acidic substance like vinegar, which has in it acetic acid, and we know the color when we have a basic substance like the household ammonia. So now you can test just about any substance that you have at home, provided it dissolves in water and also its own color does not interfere with the measurement. So I'll test now this carbonated beverage. What do you think this is going to be, acidic or basic? No, don't guess. It's a 50-50 guess, right? It has carbon dioxide in it, right? And carbon dioxide in water gives us carbonic acid. So we add this, and you see it's on the acid side. Now what about baking soda? Is that going to be acidic or basic? Again, don't guess. It's a 50-50 guess. We add some. You see it's on the basic side. In fact, if you spill some acid, you should neutralize it with baking soda. Now we take milk of magnesia. Is this going to be acidic or basic? Well, it says on it antacid, right? So let's find out. We take this. And you see it is on the, stir it up, you see it's on the basic side. Now, you know, most things that we eat, not all of them, most things that we eat are acidic. For example, lemon juice, is that going to be acidic or basic? Well, let's find out, see? There, it's acidic. Now, not everything that we eat is acidic, and not everything that we don't eat is basic. So, let's do one more. Here's Vanish, another household chemical. So, is it going to be acidic or basic? You see, it's very, very acidic. And this is, of course, whoops. This is an exception to the general rule that I told you that most of the things that we eat are acidic. You have to be very careful in handling this because it is quite acidic. So here's an example of a set of experiments you can do at home, and Santa and his elves have prepared a set of instructions for you to carry out this experiment at home. And now it is my pleasure to present to you a man who is very, very well known for a very fabulous and fantastic development called Wisconsin Fast Plants. And it's my pleasure to present to you Professor Paul Williams.
Hi, boys and girls, and welcome to biology. In fact, we're going to talk about bottle biology today. Something different. Look at all these bottles. You know, I know that you're all good scientists here because already you're good chemists and already you're good physicists. How many think they're good biologists? Right. Well, to be a good biologist, you've got to be a good chemist and you've got to be a good physicist. And you know, the world of biology is very exciting because you're part of it, because you're living. And this is about the world around you that's living. One of the things that we find ourselves in this great world, is an ecosystem. And many of you like to go out and take walks in the woods and enjoy the trees. As you look in the arboretum, as you walk around, what do you see? More and more humans are doing to this ecosystem. What are we doing? We're loving it, yes, but some of us are not loving it. We are what? We're littering it, we're polluting it. We're beginning to change this lovely ecosystem. Bottle biology, which we're going to talk about tonight, is sort of the solution to pollution. And we're going to get you demonstrating some of the things that we can do with a lot of the stuff that you throw away. But I need some pollution. Is there any pollution in the room? Bucky, have you got some pollution for us? Well, good for you, Bucky. Garbage. How about it, Bucky? This is where bottle biology begins, right in your garbage can at home. And you know, I'm going to show you how you can create an ecosystem right here in your home or in your school and begin to do some interesting biological experiments. But first of all, we start with the basic ingredient. You know what it is? A bottle. Just a plain old-fashioned bottle. And here's a bottle that Professor Mr. Physics just shot the Coke out of. Remember? Let me show you the secret of bottle biology. You get rid of this Coke and you need some hot water. You start with water. There it is. And you fill this bottle with hot water. Why am I filling it? Well, because the bottom of this bottle has to come off and the label has to come off. The secret of that is filling it with lots of hot, steamy water. Not so hot that you burn your hands, but almost. Put the lid back on, and with a little hot water, just holding it the right way under your arm, you twist off this waxy glue, and it comes right off like that. Isn't that something? That's how easy it is to get the bottom of a bottle off. Now you got to get this label off, and that's also got a wax on it that melts in the hot water, just like that. Now you've got the basic ingredients for starting your bottle biology, and I need a helper. Well, you know, there's a very famous helper in this room who volunteered. He came through and said he would help me. We got to cut these bottles so you can stack them like you're seeing here. And I'm going to call on our helper. How about Santa? Yeah. Great. Santa, what you got to do is start with your bottle I'm going to show you. All you need is a pen like this. Santa's holding that, and you want to make a ring, because where you cut this bottle is very important. And in Santa's Christmas presents to you are all the instructions on how to do this. So you just take that and you hold your pen here and you just turn the bottle and you make one ring there and another ring here, just like that. And then you take a little knife or a razor blade. Got to be a little careful with your knife, and you puncture that right on that line. Cut it like this. And here, you see, just cut it like that. Then all you need is a pair of scissors. With your scissors, you just go into where that cut is and you cut on the ring. You remove the bottom and you got yourself a nice little kind of a cup there. See? And then you go in here and you cut on this ring. And Santa, would you hold that edge of the bottle for me? Thank you. You're a terrific helper, Santa. You must also have helpers. Santa has many helpers. This is all you need to get into bottle biology, boys and girls. Santa, thank you very much for that help. How about a hand for Santa? Thank you. Now what you want to do is take this top of the bottle that you took off and put it inside the bottle like that. And it comes down toward where you left a little shoulder. And you see what you've got is a little unit like that. This has got a little shoulder on it, and you can begin to stack this, just as we have here. And you can go on and on and on, as high as you want to. And that's what we're going to do right now. We're going to begin to build an eco-column, which is a miniature ecosystem. Where do you start when you walk outside? You start on the ground, on the soil. And so we have the soil. But did you know that below the soil, where you are walking, is water? Groundwater. So basically, soil and water are related. And you can see there's water in this column below the soil. Things that happen in the soil can influence the water. So if you make pollution in the soil, frequently you pollute the water downstream or in somebody else's pond. But if you look here, we're just going to be placing this column on a little platform here. And a little bit of Velcro tape is amazing stuff, because it lets you stack this column. So that's the beginning of an eco-column. Now, this is a subset of an eco-column that you can do experiments with. So you see the water below and the ground above is what we're talking about. Things that happen here in our farmlands and our gardens, too much fertilizer, can be studied so that they're influenced in the lake. You've all seen how green and sort of yucky Mendota gets. It's because we put too much fertilizer in the farmland adjoining Madison. Once you go above the ground level, we find that all sorts of things happen on the surface of the soil. Most of the activity of humans is to throw that pollution on the top. Some of it, we have to find very big holes to bury in. These are called landfill sites. Some of us who are home gardeners like to compost. And so by cutting these bottles and stacking them up, we have a leaf litter layer, a compost column. And that just fits on top of the soil. So that things that are happening in the compost column also affect the water because they're connected. Now let me show you what happens in compost boxes. There are little snails and all sorts of things living in that compost column. Well, let's show you how you make a compost column. Over here is an empty compost column, and over here is one that is filled with compost, and it's an experiment by a student who has got in this one maple leaves. And he's pouring water into that and seeing how quickly the maple leaves will turn to good humus. Another compost column, which he's comparing, are black walnut leaves. And he's asking the question how the two are comparing. Well, here's a compost column that's about 1.5 years old. This was filled last year. And look what's left of it. Where do you think it's all gone? In the water. It's gone in the water. But it's also gone to carbon dioxide. Anybody want to have a sniff of this compost? Come on, Bucky. Santa? He's a chemist, you see. How about a sniff? Anybody? Anybody want a sniff? Not bad, huh? Well, take a look at it. You can come up a little later. Maybe you can sniff it. This is the next layer. Now, up above the compost, of course, is the soil. And here are some of the fast plants. These are 14-day-old fast plants in full flower. And you can see that things that go on in the fast plant world influence what's below. Above this is a little system we call upstairs, downstairs. And here we have a praying mantis, because flies are generated in the compost column. And if we pack that praying mantis in here, why, he needs food. And the flies just come on up through the garden here, and mantis is there fat and sassy feeding on that. Now, in a natural woodland in Wisconsin, we have lots of holes and ponds. And on the top of the pond, of course, is a little lake. What we want to do here is make it rain. And so here's what we do. Why does it stop raining? Physics will tell you that. But by just making it rain in here, you can see it rains all the way through the column. This is how you can build an ecosystem. Now, to make an experiment with an ecosystem, you've got to ask a question. What happens, for instance, in this experimental system, and this is your test for the night, if you add acid rain? We put in some of Professor Shakhashiri's cabbage juice into this section of the compost column. What color should this turn if this is acid rain? Red. Let's see what color it turns. See if this is acid rain. Well, that means that the rain is acidic. You've done an experiment. Well, we're going to just break now, but what we want to do is ask you one question before we leave. Are there experiments that you can run in an eco column? Thank you very much, and we hope you enjoy it.
Thank you very much, Professor Williams. Again, you can see that we have very exciting research and very exciting teachers at the university. And someday, all of you, I hope, will come to the university and study science. You know, we do research in science in order to understand the mysteries of nature, in order to have fun, as my shirt says. You know, science is intellectually stimulating, and it is emotionally rewarding. And that's why someday, I hope that many of you will get to be scientists, become scientists, mathematicians, or engineers. And I know most of you will not, but I want you to have an appreciation of science. And so for our special ending, I'm going to do one experiment in this very special glass contraption. It looks like a spiral. I'm going to take a clear blue liquid and mix it with a clear colorless liquid. We're going to do this in the dark. So let's do this in the dark and see what happens. Ready? Here we go. This is chemiluminescence. This is the release of energy in the form of light, but not in the form of heat. With the lights on, please, you see that the color that is emitted is characteristic of the chemicals that we use. And Santa and his elves have put a special chemiluminescence experiment for you in the bag that you will get as you leave. I want to close by thanking you for coming to my laboratory this evening, and I wish you all a very, very happy holidays. So long.
Have yourself a merry little Christmas. Let your heart be light. From now on, our troubles will be out of sight. Have yourself a merry little Christmas.